So let's look at how we could use Taylor series to approximate a definite integral. So here I've got a definite integral from 0 to 0.1 of cosine of x to the fourth. The problem being this function has no antiderivative. So I can't use the fundamental theorem of calculus. I can't just take the antiderivative, plug in 0.1, plug in 0, and subtract. So you could use a method from Calc 1 like rectangles or trapezoids or Simpson's rule. The problem is that's going to require you to find a bunch of points along the curve, right? You have to break it into subintervals and evaluate at certain points. But we've been talking about how cosine is a transcendental function and finding values of it is difficult, right? So you would be doing a bunch of approximating within that, right? So we'd like to avoid that. Let's assume we can't do infinite precision calculation on each one of those points. What could we do? And what I want to do is replace this function with its Taylor series. So let's remind ourselves, first of all, cosine. We know now that cosine x is identically equal to its Taylor series everywhere, right, for all values of x. So we could really do this on any interval because it's always true. Cosine x equals its Taylor series. And I'm not going to write sigma notation. For what we're doing, I think it'll be easier to follow if we just write out terms and then dot, 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 right? So I am within my rights to interchange these two statements anytime I want. So that means if this function equals this, when I plug in x to the fourth on the left, it should be equal to plugging in x to the fourth on the right. Now, I've set an error bound of 10 to the negative 12th just as a sort of arbitrary, fairly small value there. I don't know how many of these terms we're going to actually use. When we finally get down to the end and do our evaluating, we're going to have to truncate this because there's infinitely many terms. And where we truncate this is going to depend on the error that we're looking for. So for right now, I'm just kind of writing out the details of the first few terms. I don't know if that's enough or not. Although, to be honest with you, in the textbook homework, they are nice enough to us to not make us require 6, 7, 8, 9 terms. Usually it's going to turn out that the first 2 or 3 terms is going to be enough to get the error that they ask for. So they don't punish us with a long computation. OK, so that means that because this function and this series are interchangeable, I can say that this integral from 0 to 0.1 of cosine x to the fourth is identically equal to the integral from 0 to 0.1 of that. 1 minus x to the, and I'll go ahead and simplify those exponents and those denominators. 4 factorial is 24, and so on. Now, because I've got the dot, 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 that's implying that that's the entire series, right? So there's no approximation yet. That's an equal sign there. Those two things are identically equal. Now, term-by-term integration theorem put to use now. We know how to integrate this thing. We just go through and integrate the terms. So this should be equal to x minus x to the 9th over 18 plus x to the 17th over whatever 17 times 24 is. And I'm not even going to bother calculating that, and I'll tell you why in just a minute. And on and on. OK. Notice, and I'll harp on this all the way through, so far there's no approximation. That is identically equal to that. Term-by-term integration theorem, this is identically equal. There's no error yet. Now, fundamental theorem of calculus. We're going to plug in 0.1. We're going to plug in 0. So over here, I'll say that this is then identically equal to 0.1, 0.1 to the 9th over 18 plus 0.1 to the 17th over 17 times 24, and so on, minus, now this is nice, when 0 goes in, it's 0 minus 0 plus 0, and so on. Now, still equal, right? Because of the dot, 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 this is identically equal to that. Now we have to approximate. That's where our error bound comes in. Now notice this is an alternating series. So I'm going to use alt series error estimation theorem. Remember that says that my error bound is always less than my next term, or my next u, so ignoring the plus minus. So what I want to do is search through here till I reach the first term that's less than 10 to the negative 12th. And there's a method to our madness here of using this as an upper limit. This makes hand computation really easy. That could be any number, but making it 0.1 makes it simple because what is 0.1? It's 10 to the negative 1. So this is 10 to the negative 1. This is 10 to the negative 9th divided by roughly 10. So that's in the neighborhood of 10 to the negative 10th. Not quite small enough. That number on top is already 10 to the negative 17th. It's already smaller than that, and it's being divided by some big number. So this is definitely less than 10 to the negative 12th. And now you see why I didn't bother multiplying these together. It's not going to really matter because this term is definitely less than 10 to the negative 12th. So all I'm really going to need to use are those first two terms. So here's where the squigglies come in. This is now approximately. Now this thing I know exactly. 0 plus 0 plus 0 plus 0 plus 0 forever is 0. So no error there. But I do introduce error when I stop at that term. So 0.1 minus 0.1 to the 9th over 18. And then I want to state why I know I've achieved that error. Well, I know that my error magnitude is less than my next term, 0.1 to the 17th over 17 times 24. But that's definitely less than 10 to the negative 17th, right? Because that's 10 to the negative 17th divided by something big. And clearly that's less than 10 to the negative 12th. So here's our approximation. That integral is approximately equal to this. And we know our error is definitely less than what we wanted there. So I want to see both those. I want to see you truncate, and I want to see you argue why that's what you wanted to truncate at. Right? Why is two terms good enough? Because the third term is less than 10 to the negative 12th. And by alternating series error estimation theorem, our error with an alternating series is less than the next u, which in this case was the 0.1 to the 17th over 17 times 24. Now, the numbers in here are set up, and your homework will be the same way to make this easy to analyze quickly. Right? I was able to analyze that this was less than 10 to the negative 12th without really doing any computation. This might be a little tricky to finally simplify. That's why I just leave it like this. What I want to see is that you use the right number of terms and you make the right argument about your error. Don't worry about simplifying that expression down.